get set up from current slide. And then finally, let's go over the announcements. I think I've told you before about the Alabama A&M has the North Scholarship Program for people interested, or at least interested in investigating the possibility of teaching math or science. So that's that one. The next ones are my next 3 Fridays are different from what my normal schedule, and actually the last Friday was too. Last Friday I was here on this campus because I had to make up a class, and so I wasn't on the Birmingham campus. This coming Friday, I have a doctor's appointment that starts at 9:15, a really inconvenient time. I wish it would be early or late, but not right in the middle. But anyway, so I don't know for sure if I'll go to Birmingham before the appointment or just work at home and then head there after the appointment's over with. I'm going to head there anyway afterwards, but whether I go there before, I would drive 30 minutes, be there 45 minutes, and drive 30 minutes back to the appointment. That just doesn't quite seem reasonable, but if I need to, I will. And then after the appointment, I'll be there as long as necessary. I just don't know what time I'll get there. So that'll all be on the Birmingham campus when I do get there. Yeah. Now, secondly, the next Friday, I'm not on either campus at all. I've got a meeting, articulation meeting they call it, down in Mobile. So I've got to drive approximately 4 to 5 hours to get to Mobile, spend 3 hours in a meeting, and then 4 to 5 hours driving back to Birmingham. So that's a pain in the neck. 8 to 10 hours of driving to attend 3 hours of meeting. But I've been told I'm supposed to do it, so I'm going to be there. The following Friday, I have an eye appointment, and that's right across the road here at UAB West, so I don't have to go very far. Actually, I'll drive here to campus. The appointment's at 8:15, so I'll be there. I'll try to be here at campus before 8, get over there, find the place, and get my appointment done, and then head to, then I'll either stay here on this campus or I'll go back to Birmingham, whichever. So we'll figure that out. Okay. I don't know of any other major announcements, but those are the ones I do know about that are happening soon. Any questions on anything up till now? All right. We're in Chapter 2, which is first order differential equations. 2.4 are exact equations. We just got started with them, talking about what they were. Let's talk a little bit, this is the top of page 65, about the differential of a function of 2 variables. I think I've been talking about this, but the book probably hasn't placed all that great of emphasis on it. So here's what they're talking about. Let's just imagine that we have a function, let me get my pen set up, a function z. Z is equal to some function f of x and y. So x and y are both independent variables to some extent, and z is a dependent variable on both of those. Function of any of 2 variables with continuous first partial derivatives, okay? In some region R of the xy plane, okay? Now, it says, recall from calculus that its differential is defined to be this. dz is the partial of f with respect to x times dx plus the partial of f with respect to y dy. Now, just to get you reoriented to partials. Remember, this is ordinary differential equations, but I said we would still be using partial derivatives, not so much partial differential equations, but just partial derivatives. Here's one of the places we'll use those. This is z is a function of 2 independent variables. It's perfect differential. So the d is not a partial d. This is the differential of z. So that's a dz. Those are partials. f has two independent variables, so to do a derivative there, it has to be a partial derivative. So partial of f with respect to x, then that's a dx, because x is an independent variable, so that's a dx plus the partial of f with respect to y, dy. So those are partials, and the three in between are actual d's, derivatives. Okay. Now, what if we had a special case that this f was some constant function, c? Okay? Then what you would have, the dz would be 0 because it's a constant. So that's a 0. I'm going to put it on the other end. And now what we have is partial of f with respect to x dx plus partial of f with respect to y dy is equal to 0. Okay? In other words, given a one-parameter family of functions, f of xy is equal to c, we can generate a first-order differential equation by computing the differential of both sides of the equality. Okay? For example, so here's the better example, or an example. I think I'll do this on a clean sheet just so we don't get them crossed up. Okay? X squared minus 5xy plus y cubed is equal to c. That's some constant. First, one parameter system. Some combinations of x and y are always equal to a constant. Okay? Now, what we're going to do is, if we do our derivatives, okay, the partials, okay, the partial of this thing here with respect to, I'm not going to write it, with respect to x dx plus the partial of that thing there with respect to y dy is equal, and partial or derivative of 0 of c is 0. Okay? So the partial of that thing. What is the partial of this thing? This is 2x
minus 5y.
5y. And the other part doesn't have a part, so that would be that dx plus, now the partial of this with respect to y. First term has no y in it, so that's 0. Next.
So we're never doing the partial of y?
Yeah.
Doesn't have anything, it would be minus 5x.
Minus 5x.
And it would be 3y squared.
Plus 3y squared. dy is equal to 0. There's a differential equation. Okay? Now, we call that an exact differential equation because we took the derivative of that function, you know it's exact. Okay. So here's the definition. And here's also a warning. Okay. Of course, not every first-order differential equation written in differential form, and you can write it like this, m of xy dx plus n of xy dy equals 0. Okay? Just because it's written that way, that doesn't correspond to a function f of xy equal to some constant. No. You could just randomly pick a m of xy and n of xy, and it had nothing to do with any function equal to a constant. But one that is equal to a constant can be written in that way. Okay? So it goes one way but not the other. Okay? For our purposes, it's more important to turn the foregoing example around, namely if we are given a first-order differential equation, such as what I just wrote above this one, is there some way we can recognize that the differential expression is the differential of, that this expression is a differential of this? Okay. If there is, then an explicit solution, then an explicit solution of this thing, of this equation, is that thing. Okay, I'm sorry. They write this and that in there, and they're not real clear what they're referring to, but that's what it is. So, actually, they're asking a question there. If we're given that, is there some way we can recognize that? I'm sorry, I was misreading the question. Here's what the definition is that sort of answers that question. Okay. A differential expression, m of xy dx plus n of xy dy equals 0. A differential expression that, oh wait, I'm sorry. Expression, not an equality. So take out the equals 0 expression. I wondered why they were using expression rather than equation. But if that expression, that a differential expression such as that is an exact differential, there's the definition now finally, exact differential in a region R, in a region R of the xy plane, if it corresponds to the differential of some function f of xy. Okay, defined in R. Okay, in that region R. So, a first order differential equation of this form, m of xy dx plus n of xy dy equal to 0, that's your differential equation, first order differential equation, is said to be an exact equation if the expression on the left-hand side is an exact differential. If this thing on the left-hand side an exact, I can't write, differential. Okay, so that's what it boils down to. Can you determine that? Okay, now let's go to a clean sheet. X squared y cubed dx plus x cubed y squared dy, x cubed y squared dy equals 0, is an exact solution because the left-hand side is an exact differential of, now let's just make a guess on this one. I'm going to guess, you got a 1/3 in there, we'll see why in a minute, x cubed y cubed, okay? Because if you take the derivative of that, you get, first with respect to x, you get a 3 times 1/3, which is just 1, x squared y cubed, dx, that's the partial of this thing with respect to x, plus, and you take the partial, the derivative of this, that would be the partial of this thing with respect to y, which again be x cubed y, okay, dy. And that is exactly what we've got above. No, x cubed y squared. I left off my square term. Sorry. Eyes hurt. All right. Now, so in this case, this part right here is what we call our m of xy, and this part right here we call our n of xy. Okay? So, let's come up with a theorem here that's going to list these criteria, that what makes an exact differential. So again, we have an m of xy and an n of xy. Let them be continuous and have continuous first partial derivatives. PD is partial derivatives. My screen is flip-flopping on me some. Have first partial derivatives in a rectangular region R. Okay. Defined by A is less than X is less than B, and C is less than Y is less than D. Sort of sounds like Cal 1 or Cal 2 all over again, doesn't it? Then a necessary and sufficient condition. Now you'll see this a lot in math. Necessary and sufficient condition that m of xy goodness, I can't breathe, dx plus n of xy dy is equal to 0. No. Again, the expression. I'm sorry, I keep wanting to make it an equation. That expression for that to be an exact differential, is this. Yuck. Partial of m with respect to y must equal the partial of n with respect to x. That's what's required. So if you have any old given m of xy and n of xy written as a partial, as if it might be an exact differential equation, here's what you do. You test it. Now, notice here, this is the variable coefficient of your dx. That's your variable coefficient of your dy. Okay? Take the partial of this one with respect to the y and see if that's equal to the partial of that one with respect to x. If they are equal, we have an exact differential on our hand. If they're not, they're going to give us some hints later of what we might be able to do. So let's first deal with the easier case when they are equal to each other, okay? Therefore making an exact differential. Okay, now remember, this is not solving the problem for you. This is just determining whether you can solve the problem using these techniques or not. Okay? Now they do a little proof here, and it's probably a good idea to read through and understand that proof. So here's how we go about it. So that's the first step. Make sure it is an exact equation. If it's not, don't even try this stuff until we get something a little bit later. But if that holds, then we start the process. And the process, that's just a test. We sort of forget about that for now, and here's what we do. All right, oops, that's not what I meant to do. I meant to do this. Okay. Sorry. Man, I was telling my last class, I had some, I like to eat, use the salad dressing of barbecue sauce. It just has a lot more flavor than most dressings do. But we went to a new barbecue place that's just opened in our neighborhood, and it's really good. And we got 3 little things of their sauce, and my wife was eating more of that than I was because I had some other older things I wanted to eat up. She sure wasn't using much sauce, I didn't think. And I had some too, but I had, just put a little sauce on too. I hadn't really noticed it. But last night when I was fixing my lunch, I just took that leftover barbecue sauce and put it on my salad like I always do. Whew. This had some high test. Okay, it had some heat to it. Yeah. And boy, when I was eating my salad today, all my sinuses just started draining. And therefore I'm a little nasally sounding. I know I have to be today because I've just been blowing my nose ever since lunch.
Who needs nasal treatment when you've got copious amounts of capsaicin?
Yes, that's exactly what it was. And they had copious amounts in it. Oh, my word. I know it's not good to drink water, but that's all I had on hand. Yeah. And I just kept
fatty stuff like milk is what gets that off.
What's that?
Fatty things like milk is what gets that off.
Yeah, right, exactly. I didn't have any handy, so I used what I had, which basically just sort of spread it around a little bit. But, yeah. Oh, my goodness. It was good, but, man, it had more heat than I was thinking. So it just got in my head.
I have a pretty high tolerance for it. I mean, some stuff surprises me time to time.
Right. I've been to one Indian restaurant that they fixed the dish hotter than they normally did, and I mean, the tears were coming. It was good tasting, but man, yeah. And this too, goodness, my head is so clogged up.
Yeah, I would normally, well, depends on the restaurant you get it from, but I can usually eat like whole blobs of wasabi that would get you for your whole meal. I'm like, oh, how about that? But there are some restaurants, they leave that stuff sitting or something, and it starts to dry up into like crystals.
Right.
And it gets so hot, even using it normally, it can't even stand it.
Oh, wow.
It's crazy. I don't know what some of the restaurants are doing to it.
Huh.
Yeah. I learned if it doesn't look smooth,
don't do it.
Try it.
Okay.
Don't try it.
So, that was the test. Here's how we go about. Now, I want you to think back when we're doing linear. We had all that stuff. You take a derivative, you raise it to the e, you do this, do that. Well, after a while, it got into a rhythm, and you were doing it.
Yeah.
This is almost the same way. You almost feel like you're going in a circle again because you're doing this, you're doing that. So bear with it. You'll see it comes out all right. Okay? You start off, okay, you're given the equation, okay, m of xy dx plus n of xy dy is equal to 0. First thing you do your test. Do the partial of m with respect to y, do the partial of n with respect to x. If they come out the same thing, there is a function that this will work. If they don't, wait till later in the section. There may be some things you can do to adjust. But for now, hang it up, okay? This method will not work, okay? So, if the test works, okay, then you assume there is some function, here he is.
We've added another 33 continuous percent to the class.
Yes. You actually doubled the class size. Okay.
Of students.
Yeah.
I was thinking people in the room.
People in the room, right. I get bigger numbers if I talk about class size. Okay. All right.
50% increase in attendance.
Yeah. All right. What we're doing are exact differential equations. Okay. We started this last time. We've done some other work with it now. And here's what the deal is. Just because it looks like that doesn't guarantee it's an exact equation. Okay? And you'll get to the term exact later. You've already sort of hit it, so listen to YouTube and you'll see why. But the test to see whether this is an exact, do the partial of this coefficient of two variables, x and y, do the partial of this with respect to y, and then do the partial of this one with respect to x. If those two partials come out the same, then this is an exact equation. Okay? So, then you assume, and I guess when nobody was in the room, I just abbreviated, maybe since you came in, I better write it out. Assume, then, f is this function that this is an exact differential for. Okay? There's got to be that function f. Okay? We don't know what it is, it's just some function f. Okay? Well, from what we were doing before, and coming in the middle, you just have to take my word for it. What we did, they gave us a function. We took the partial of that function with respect to x dx plus the partial of that function with respect to y dy, and the function was equal to a constant. Took the partial derivative of a constant is 0. That's how you get this. So we've just shown that if the partial of m with respect to y is equal to the partial of m with respect to x, that's your test. If it is, there is some function f that when you do that derivative. So let's take that f that we know is out there, we just don't know what it is, and do the partial of f with respect to x. Now when we do that, that's going to be this term right here. So that's going to be your m of xy. Because that's what we did. If we were given a function of alpha of xy, took the partial of that with respect to x, you got the m dx, and then the partial of that with respect to y, that's your n of xy dy, that would be equal to 0. If that function was a constant, then that's what you get. So you know that's going to be the case. The partial of alpha with respect to x is m of xy. Okay. That's what it would have been. So what we do now is this. That doesn't quite seem legal, but we're going to do it. Okay? It makes sort of sense anyway, doesn't it? And then we're going to integrate this. Okay? Well, the integral of a derivative is f. Okay? But this is an indefinite integral. And you're integrating this with respect to x. That means treat the y's as if they're constants. Okay? So this is going to give you this thing. The integral of m of xy dx, whatever that is. Okay? When you actually have functions in there, it's easier to do than this. Okay. And then, because when you integrate, and it's an indefinite integral, you got to put the constant there. Okay? But it's not just a c anymore. Because this, we're integrating with respect to x, you're treating your y's as a constant, so this constant may be some function. I think they use g of y. Because you see, you're only integrating with respect to x, the whole function g of y would be counted as a constant. Okay. So that's what you know your f is going to be. Now, this is some function. You integrate that with respect to x alone, and then you add some g of y to it. Well, that's your f. But we don't know what it is, but at least it's getting a shape on it. Well, the other half of this is that the partial of f, just like before, This f now, that we have a little bit more idea what it is with respect to y, has got to be this n of x. Y. Okay? Now, if you take the derivative and partial of this, now remember, this looks like an integral, but you've actually integrated. It's some function of x and y. Okay? So this is going to be d by, or partial with respect to y of this integral, m of xy dx, plus, and when you take the partial of g with respect to y, it doesn't have to be a partial. That's only a function of y, so this would just be g prime. dg dy. Okay. Derivative of g, which is a function only of y, dy. Okay. Now, that's going to be your n of xy. Now, you know this, that was given in the problem. You calculated this part, and then you take a derivative of that, so you know that part. The whole problem comes down to identifying what this is, because that was the unknown function. It's just like solving for c, but now it's solving for that derivative. So, I've run out of room. Let me start over at the beginning. I've taken way too much space here. Okay. So now this g prime, which is dg dy, is equal to, and what we're going to do is take the n and subtract from it this derivative here. That'd be n of xy, which we knew, that was given in the problem, minus the derivative with respect, partial with respect to y, of the integral of m of xy dx, okay? That's going to be what this is, okay? Now, if you feel like you're getting dizzy here, there's a reason for it. It really is true. So what you're doing now is integrate that with respect to y. In other words, multiply both sides by dy. You know, make it right in differential form, okay? All this is to get that g, okay? And this will give it to you. Okay, so let me erase this. All right. So you integrate that, integrate this, and integrate that. Okay, and that looks like a double integral. It really isn't, because you've already evaluated that. We just don't know what it is now. So this gives you your g of y. And they don't even write it anymore. That you just integrate those functions you have with respect to y, and you only have the y in it. There's no x's left there, okay? And then you plug that back into what you had before, and that gives you your f of xy. Now, I know it's a lot of blah, blah, blah. But before we actually do a problem, they say some observations are in order. First, it's important to realize the expression n of xy minus that derivative there, that thing in the integral here, this thing right here, okay? There, that thing right there, is independent of x. We have these x's in there, but it's independent of x, okay? And it seems hard to believe at this point, but it is. So, secondly, we could just as well start assuming df dy, okay, I've already erased it. You know, we started with partial of, the partial of f with respect to x was m of xy. We could have started with the partial f with respect to y was n of xy. Either way, do whichever's easier. That's the key, okay? So we could just, okay, and after integrating n with respect to y, then differentiating the result, you'd find that everything comes out about the same. Do which one is easier. Now, all that's been with letters in there. We never do an evaluation. It just gets more and more complicated. Let's actually do it step by step with numbers in here. I mean, with functions in here. All right. Here's one. 2xy dx plus x squared minus 1 dy is equal to 0. Okay. Now, looking at that, I almost can on this one, but just looking at that, it's not intuitively obvious whether that's exact or not. Don't assume just because it's written in this form it's exact. Okay? So, our first is the test. What's the test? Do the partial of this one. Okay, now we're not doing partial differential equations. We're using partials to solve ordinary differential equations. Okay. Partial of 2xy with respect to y, always the opposite one. See if that's equal to the partial of x squared minus 1 dx, again, with respect to the opposite one. Okay? Well, what is the partial with respect to y of 2xy? No, the derivative, okay. Okay. This is assuming this function here, in parentheses, is a function of y, okay? Which obviously there is a y in there. We're going to take the partial with respect to the y, treating the x as if it's a constant. That's the key with partials, okay? So assuming x is a constant, 2 is a constant, so that's just a constant times y. What's the derivative of a constant times y? Just a constant. And that, in this case, that's 2x. Okay? Now let's do the same thing over here. Take the partial of this with respect to x. And what's that? 2x. And those are the same. Okay? Meaning that, yes, this is an exact differential equation. So the first part here is just a test. If it passes the test, then you can proceed. We passed the test, we can proceed. Okay? If we didn't pass the test, then either hang it up or go back, and later in this section we're going to see what to do if you fail the test, but can you fudge around with it a little bit to make it pass the test. Okay? So, we passed the test so we know it works. Okay. Next step. Now we can do it either way. Let's do it the way they said it to begin with. Let's assume there is some function f that this is an exact derivative of. Okay? Then the partial of that function f with respect, and by the way, the f of xy will be equal to a constant. That's when you took the partials of these, you get this side. When you take the partial of c, you get a constant. You get 0. So this is what we're looking for. That's going to be a one-parameter system with x, y, and there's your parameter, c. Okay. So let's take the partial of that with respect to y, x first, okay? And we know that's going to be 2xy, right? Because that's what your m of x was, okay? That's your 2xy. All right? This isn't quite fair mathematically, but they do it, so I'm going to do it too. Let's integrate both sides of that. We first wrote it as a differential, and then we're integrating it. Okay? So the integral of this is just some f. That's your function f, function of x and y, that we're going to wind up with. That's what we're wanting. Okay? Now we're integrating this only with respect to x. So what's the antiderivative of 2 times a constant times x? Now you're integrating this time.
What was your question?
What is the integral of that? The antiderivative of this thing here only with respect to x. So in other words, the y is just some constant. So 2 is a constant, y is a constant. You're just integrating a constant times x.
Y over 2.
Okay.
Y squared over 2.
Okay. Okay. You're pretty close. It would be your 2y. That's your constant. X squared over 2. You're right. But the over 2 and the up 2, they cancel out, so it just be yx squared, or x squared y. By that? Okay. So that would be x squared y. You just integrated it. Now, if you have any doubt, take the derivative. Partial of that with respect to x, you get 2x squared y. Okay? So yeah, that was the right answer there. But this is an indefinite integral, so you have what would have been a constant, but now it's a function of y, because y was treated as a constant, right? Okay. So this is what your f of xy is going to look like. The trouble is we don't know what the g is. So we have to figure that. All right. Well, just like the partial of f with respect to x was your m, the partial of this f with respect to y is this thing over here, right? So let's take the partial of this with respect to y, okay? Now, if you do that, you also take the partial of this with respect to y, okay? Now, and this answer is supposed to be our n, which is x squared minus 1. Okay? That's supposed to be the n. We don't need the parentheses. Well, we might, so let's leave it alone. So this is what that's going to be. That's over there. So let's take the partial of this. What's the partial with respect to y of x squared y? Second?
So we're treating x as if it's a constant.
Absolutely.
So that's going to be y squared.
No, not y squared. Taking the derivative with respect of y, that would be like a constant times y. This derivative would just be the constant, right?
Okay.
And that would be x squared. Okay? And this would then be plus dg dy. That's just, you don't need a partial there because that's all only got y's in it. So you can write it as a total derivative, a derivative. Okay? And this is supposed to be equal to x squared minus 1. Okay? Now, we definitely don't need our parentheses, so let me get rid of them. Didn't really need them here either, but they were around it there, so I carried them over. Okay. Now, simply subtract x squared from both sides. We're trying to isolate this, okay? So these go away, those go away. So what do we have? dg dy is equal to minus 1. So, just like we've done before, let's integrate that baby. In other words, move our dy over here, and the integral of this, well, I'm just going to keep that on the outside, and this will dg of y is equal to, and this is just this. What's the antiderivative of the dy? Or 1 dy? Oh, yeah, dude. Why? Because you take the derivative of y, you get dy, right? Yeah, so that would be y. Now, on this one, do you need a constant of integration? Okay? They say not. Okay? Because your constant is going to show up here. So if you brought one in, you're going to have to combine it with that one. So don't mess with the constant of integration. That's your g of y. Okay? So go back to this step before I did the partials, right there, and before we put that back in. So I'm going to write it up here. I'm sorry I didn't leave enough room at the bottom. What did we have? F of x, y is equal to x squared y plus g of y, but the g of y is minus y. There we have it. Okay? And you see that is equal to c, because f of xy was equal to c. Okay. So x squared y minus y equals c. That is your solution to this exact differential equation. Now, this is somewhat implicit, but you see the y's exist as y's in both of those, so you could factor out a y and leave you an x squared minus 1 equals c, and then divide both sides by x squared minus 1. And then you have y is equal to c over x squared minus 1. And that would be your one parameter explicit solution to this equation. Okay. Now, I would just as soon as do it like this, okay, because then you can check it by taking the partial of this with respect to x, the partial with respect to y, and you see that you get exactly those things here. Okay? So, to me, that's just as good a form, but they actually wrote it this way. Now, things to note again is obviously x can't equal plus or minus 1. If it did, this makes no sense at all. But then also, if it did, then that side makes no sense. That would be a 0. So you just have 2xy dx is equal to 0. Well, you could integrate both sides of that, and you get x squared y is equal to 0. Well, either x is 0 or y is 0. It sort of goes in circles there. X couldn't be, then your y would have to be 0, because x was obviously plus or minus 1. That's where you started. But the only way to get that equals 0 then would be y would be 0. So the whole thing makes no sense. That differential equation would be 0xy plus 0 dx plus 0 dy is equal to 0. Yeah, big whoopee, okay? You know that had to be 0, so that's not really much of a solution. They would say that's a singular solution or something like that. Let's see if they do anything. Is defined for any interval not containing either x equals plus or minus 1. So any interval that's from negative infinity to negative 1, but not counting negative 1, that would work. Any interval from negative 1 to positive 1, as long as you don't have either one of those in it, that would work. Or any interval from positive 1 to positive infinity, as long as you don't have the positive 1 in it. So you could not have, say, an interval from 0 to 2. That would contain, a unallowed value. You couldn't have one from negative 5 to 0. That would contain okay. And you sure couldn't have anything negative 5 to 5. That would contain 2 unallowed things. So your intervals must be restricted to not contain plus or minus 1. Okay? Now, this is not a solution here. Remember, your solution is this. F of xy is equal to c, not f of xy is equal to that thing. Okay? It's equal to c. That's the solution for your differential equation. This is how you got that solution. Your f of xy was that, but that's not your solution to it. The solution is this, one parameter system. Okay. So let's
explain the difference then, because they're saying that it's not the solution.
No, it's not the solution, but This is the solution, not f of xy. That's not the solution. This is your solution. What f of xy is equal to c.
Yeah, yeah, okay, all right. Every time you said it's not the solution, but this is the solution.
Yeah.
You had
Yeah.
highlighted x squared y.
Yeah. Right.
That's why I was.
Yeah. All right, so let's do example 2. Okay. Solve this one. E to the 2y minus y cosine, oops, I was looking ahead too much, cosine of xy. I'd like to put those in parentheses just to do that, okay, but they've got another parenthesis here, that's why they didn't. Dx plus 2x e to the 2y minus x cosine xy plus 2y dy is equal to 0. All right. Let me make sure I didn't throw something in I shouldn't have or leave something out I needed. Yeah. Too bad it doesn't have a log x in the cosine, isn't it? Or something like that. Okay. All right. Now, this certainly is of the right form. M of xy dx plus n of xy dy equals 0. All right. It is the right form. Is it an exact differential? You always have to test. What's the test? Take the partial of this one with respect to y, take the partial of this one with respect to x, see if they're equal to each other. If they are, it is an exact differential. If they're not, hang it up and go on to the next problem, okay, until we learn some more techniques. So we're going to do the partial of this, e to the 2y minus y cosine xy. That looks like a lot of fun, doesn't it? With respect to y, and it had a lot of y's in it. And we're going to see if that's equal to the partial of this thing, which is 2x e to the 2y minus x cosine xy. I didn't put that in parentheses this time. I think I will. Okay, plus 2y. That partial with respect to x. Okay. A bit of practice with our partial derivatives again. Okay. Again, this isn't a partial differential equation, but you're using partial derivatives in order to solve the differential equation because you got two independent variables, x and y. Okay. So let's take the partial of this with respect to y. What does that give you? Partial of that first part with respect to y. Well, derivative of e is itself. E to the 2y. And then our good old favorite chain rule. Take the derivative of 2y and you get a 2. Okay? So you do the outer derivative first, then the derivative of the inner part. Okay? Minus. All right. This is going to be a product rule because it's with respect to y. And part of that product rule is going to be another chain rule. Okay? So, multiple pieces here. Not quite as multiple pieces as your test was, but still multiple pieces. All right, how do you do that product rule? I'm going to put this whole thing in parentheses because of that minus sign. Minus signs are there to trip you up. Okay? That's what the only reason I put them in there. Okay? So you have to be careful. Isolate them if possible, then bring them back in if necessary. Okay. So what is the product rule for that? What's the derivative of that?
sign.
Okay, you put the minus out here, and you're keeping the y and doing the derivative of that, and that would be the sine, because derivative of cosine is minus sine of xy. But then you've got something else, x, because you have to do the chain rule. And you're doing it with respect to y, and so the derivative of the inner part with respect to y is just x. So that puts an x on the outside with the y, which is kind of good because we're going to have that up above too. Okay? So there was the first times derivative of the second, plus what?
Well, you want the derivative of the first, which is just
Is 1 times the second, which is cosine of xy. All right.
But we got a chain rule, so we're going to.
No, no, no. Not on this part. When you're doing the second part, which is this times the derivative of that, that's all there is. You're doing the derivative with respect to y, that's 1. Derivative of y with respect to y is 1. If you're doing the derivative of y with respect to x, then you would have a y prime after it. Not this one, because this is derivative with respect to y. Okay. dy is 1. Okay. All right. But now we've got to move our brackets here. So it's a 2e to the 2y plus xy sine xy minus, because the minus sign in front of that whole thing, cosine xy. Is that any way in the world that's going to be equal to the partial of the right-hand side with respect to x? Now, here's going to be another chain rule, and I can see already I'm going to run out of room, but I guess I got to do it anyway. I mean, there's a product rule. I don't know what I said. There is a little chain rule in that, but not that. Okay? So we're doing the partial with respect to x of this. Oh, no, it isn't. Oh, no, it isn't. Because this has no x in it. So everything here is a constant except for the x. What's the derivative of that with respect to x? 2e to the 2y. Exactly. Okay? So that'll be 2e to the 2y. Oh, thank you very much. That was nice. Now let's do the next part. That is a product rule. So I'm going to put the minus there that is put there to trip you up, remember? That's the only reason they're in there. Okay? Now, you got a product rule and a chain rule within the product rule. Okay? So, because these are with respect to x. What will this produce? Partial with respect to x of cosine x cosine minus xy. Yes, I can't talk.
It's going to be negative sine.
Okay, so it's the first times the derivative of the second. Is that what you're doing? So the first is the x. Derivative of the next is a negative sign. So there's a negative sign for that sign. Okay, sine of xy. But then you got the chain rule, and you're doing with respect to x. And what will that be?
And negative xy.
Okay, right. You'll have a y out there. Okay. And then the second part, with respect to x. The third part, there is none. Y is, you treat it as a constant. Partial with respect to x would be 0. For this 2y here. Oh, wait. Sorry. Second half of the product rule.
Yeah.
I forgot that.
Throwing me off there. Okay.
I'm sorry.
So we want the second half, that's going to be 1
Plus 1 cosine xy. Okay. Then the third part, derivative of that with respect to x is 0. Because 2 is a constant, and you treat y as like a constant. Okay? So what we have over here is 2e to the 2y. These two minuses make a plus xy sine of xy. And then that minus times plus is a minus cosine xy. All right, now we check and see, are these two the same? Those two are the same. These are the same. Those are the same. Yes, yes, yes. So we can do it. I was looking forward to skipping this and moving to the next. Okay. But no, we've got to do it. Okay. This was all the tests just to see if you can do it. Okay. Now let's do it. So since I don't have enough room on the page, I'm going to erase everything to do with the test. We know it's an exact differential because the test came out positive. So we'll erase all this. We're not going to need any of that. Too bad we can't use some of that, you know. Yeah. Too bad part of your test wasn't something you could use later. But no. Nothing like that. No conservation of testing materials. Okay. All right. Almost a clean slate here. Sometimes I wonder if it would have been easier just to erase the whole thing and rewrite the equation. All right. Now, again, you get to choose which you want to kind of integrate first. We see this is an exact differential. Our test showed us it was. That means there is some function f of xy that when you take the partial of that with respect to x, you're going to get this thing, or the partial of that with respect to y, you would get that thing. Now, since that got 3 terms, this has 2, I'm sort of leaning toward the 2. So, leaning toward the d by dx. Maybe a bad choice, but let's see. Okay? So this, if that is indeed true, the partial of f with respect to that is going to be this thing. E to the 2y minus y cosine of xy. Okay? Like we've done before, we'll get rid of that, write it over here as a dx, integrate this, integrate that, and see what we come up with. Well, the integral of a derivative should be the function itself, f of xy. Okay. I'm running out of gas quickly. All right. So we're integrating this with respect to x. What's the integral of e to the 2y with respect to x?
E to the 2y.
Times x, right? A constant, yeah. So it's x, e to the 2y, right? And then that minus y is just like it's a constant. Now, antiderivative of cosine of xy.
It's going to be
sine.
Squared.
Yeah, it is. It's sine of xy, your antiderivative now, right? And derivative of sine is cosine, so you keep the sine, SIG and sine the same. So that's good. But if you're taking the derivative, you would multiply by chain ruling it now by your y, because that's your constant. Here you divide by y, because it's unchain ruling it, right? You're doing the chain rule in reverse. Okay. Okay. And then these y's go out. Ooh, that's nice. Okay. But you still have some function. They always call it g of y. That's your constant of integration. Okay. All right. Now, so maybe it will help to write this a little neater. X squared, no, maybe it helped to write it correctly. Okay. Okay. X e to the 2y minus sine xy plus g of y. Okay. So that's what this is equal to. So I'll take this out just to write it neater over there. Well, that's what your f is. If we knew what g of y was, we'd be through. We don't know what g of y is, so we have to go another step to get our g of y, then come back and put it back in. So remember this. This is where we're going to come back later. But we also know that the partial of this f with respect to y is this thing over here. So the partial of f with respect to y is equal to, and if I'm doing the partial of that, I'd better do the partial of this. So let's do the partial of that with respect to y. Partial of x e to the 2y minus sine of xy plus g of y.
Sorry, is it df dy?
What's that? That's one of those little dells, you know, partial symbols. Is that the one you're making fun of? No. Oh, okay.
Is it df dy?
Yeah, this is partial of f. It's partial. Okay. That's what I'm not being able to draw very well. Okay. Partial with respect to y. That's what we're doing here. And this had better be, oh, that's what we're doing. Let's see what it comes out to be. Partial of that with respect to y. Oh, and this, like we said, had better be this thing up here. Okay? So let's see what we get. Whew. Is that where we write it in? Yeah, it is. So this is equal to that. So this had better equal that. So it would be 2x e to the 2y minus x cosine xy plus 2y yeah. This partial had better be that. So what we're going to do now, just like we did before, take the dy away from here, put it over here, integrate both sides. Okay? Now let's see what we get. Well, the integral of a partial or a derivative is just going to be what's inside. So this is just x e to the 2y minus sine xy oh, I'm sorry. Wait. This is so many moving parts here. I needed to do something else first. Well, wait, let me make sure. Oh, they went and did it the other way, but I think it's okay. Okay. I started too soon. Okay. Let's go back to this. Don't integrate. Okay. was getting a little carried away. Okay. We first need to do this derivative. This derivative is supposed to equal that. So let's do the derivative first. I was going to say, didn't pause long enough there. Take the derivative of this with respect to y, and what would that be? What's that? 2x e to the 2y. Perfect.
Negative.
Minus.
Oh, we're just differentiating. We're not integrating. Okay.
Yeah, we're differentiating, right? Cosine. Okay, x cosine, because we're doing it with respect to y. X cosine, I can't write, of xy, plus g prime. This is, in fact, I like to write it gd gy. Right. But g is a function only of y. So that's a derivative, not a partial derivative, because g is only a function of y. Okay. And this thing is supposed to equal your 2x e to the 2y minus x cosine xy plus 2y. Okay?
So now we need to solve
for dg dy. Exactly. Solve for that. Okay? Well, let's see. We can subtract those from both sides. That's nice. We can subtract or add those to both sides. They're nice. So what are we left with? dg dy is equal to 2y. Okay? Well, let's write that down. dg dy is equal to 2y. And this is where I multiply. I was doing it too fast before. dy. Now we integrate those. And what would that be? G of y would equal to antiderivative of 2y? Y squared. You don't need a plus c. You're going to have a plus c up here above, so don't sweat with that. And that's what we put in for the gy here. So here's what our f of xy from right here is equal to x e to the 2y minus sine of xy plus y squared. Okay? That's what your f of xy is. And then what that f of xy is equal to? The constant c. Okay? So f of xy was just a construct to give you something to take derivatives of and stuff because you didn't know what it was. Once you figure out what it was, don't carry that around anymore. That's not your solution. That was your device to get to your solution. That's your solution. Now, you think you can isolate the y here? In other words, write it explicitly in terms of y? Just write in here. This will be enough to tell you you can't. How in the world would you ever separate that? You can't. So this one cannot be written like the other one could, y is some function of x. No. This is an implicitly defined. Well, let's see what they got. Now, they did it the other way. Whoops, I'm not on that page yet. Okay, so they get x, wait. Did they finish? Oh, okay. They put the C on the other side. So x e to the 2y minus sine xy plus y squared. They just put the C on the other side and have it equal to 0. There's no reason to do that way rather than the other way. It's perfectly fine. So we got the same solution.
So this one is not an exact.
Huh?
You said this is.
No, this was exact. It's just you can't solve it explicitly for y. Now, I think we start next time with example 3, because I think we're out of time for today, aren't we? Okay. All right, we'll begin next time with example 3. Homework exercises here in this section. We got good progress made. Any of the odds 1 through 19 that are in the back of the book, and I think probably you can do your initial value problems 21 to 25. And stop there. We'll worry about the rest of those next time. Now, a few of those maybe you can't do yet, but do what you can. Once we get more covered, then you'll probably be able to do the rest of it. All right, good deal. Today, I've got to leave sort of early because, not early, I just got to leave because I have a class on the other campus. So let me end the